This is a lecture on examples and clarifications of some of the vocabulary words in Chapter 8. So what we're going to start with is the example in your book. It is 8-1, but in a different order with some other stuff that I have included. A teacher feels that if an online textbook is used instead of hard book, it may change the student's scores on the final exam. In the past, the average final score for the students was 83. So a couple of things that I'd like to point out. The fact that we're talking about an average, this means that it's an inference about a population proportion. The information that they gave us has to do with the previous study. So this first highlighted piece of information will give us the setup for our null hypothesis. The null hypothesis says that there is no difference between the statistic, the information that we have, with the existent information. So in this case, we're going to say the actual mean is 83. It is what it is. Now, the alternative hypothesis has to do with the opposite of this. Now, the opposite of this, we need to read in very closely to figure out whether we're trying to prove that the online textbook increases the student's scores, decreases the student's scores, or in this case, changes. Now, the word change means that I have no idea whether the scores will increase or decrease. So in this case, the symbol that I have to use for my alternative hypothesis is not equal to. So this is my setup. We are using a normal distribution. So I'm drawing a normal curve. The mu of 83 is going to go in the middle. The test statistic will indicate where the sample is placed, but that would be something that I do in the next section in 8-2. 8-1 is just the setup. What I need is, I'm also looking at this alpha. Let me highlight it another color. So I have an alpha of 5% and a not equal to sign. The not equal to sign will indicate the fact that it's a two-tailed test. Now this is another vocabulary word. If I'm not sure whether it's a less than or greater than, where I have to put a not equal to sign, my test becomes a two-tailed test. What it means is my critical region consists of two pieces. So the critical regions are your tails. So if I have an alpha of 0.05, means that I have that 5% split up into two tails, meaning I have 2.5% on one side, I have 2.5% on the other side. If I have 5% on both tails, this would leave in the middle the 95%. Notice that the picture for a two-tailed alpha 05 looks exactly like a 95% confidence interval. The information and the results will be or should be about the same. So you get slightly different information, but the result of reject the null hypothesis versus do not reject the null hypothesis are the same between the 95% confidence interval and a two-tailed test of 05 alpha. These places right here is the critical value. in order to find the critical value, these are your z-scores if we're looking at the standard normal curve. What you can do is you can go into inverse norm, and what you're basically trying to find is how to cut off the bottom 2.5% or the top 2.5%. So if you put in the bottom 2.5% with a 0, 1, what you will see is it'll give you that z-score, the critical region, that will cut off the difference between the critical number or the critical region and the non-critical region. Now you'll notice that the same numbers occur over and over and over, like 1.96 and 1.645 and 2.57 to 2.58, depending on which book you're using, or 2.575. So at this point, the book does include that. So those three numbers, they will occur over and over and over the same. So you'll get to know the four numbers or the three numbers, and those will actually be given to you on the test. So I'll show you a formula sheet that is going to be provided. But those are a lookup. You can look those up under inverse norm function whenever you're using a standard normal distribution. So the 8-1 is just basically asking you for definition. So this part is called non-critical region. And the tails are called critical region. In 8-2, we'll draw this picture again, and then depending on the test statistic, we'll either fall into the critical region where we reject the null hypothesis, or we fall into the body of the problem in a non-critical region where we fail to reject the null hypothesis, and that will be discussed in 8-2. What I want to do is I want to move on to the next example to see if we can set up those alternative null hypothesis and the alternative hypothesis. A researcher studied gambling in young people. She thinks those who gamble spend more than $30 per day. So the $30 is my average that is given to me by a previous study. So your null hypothesis will always have an equal sign. It must have the parameter, in this case mu. It must have an equal sign, and it must have either the next parameter in chapter 9 or chapter 8 inclusive value. The alternative hypothesis must have a parameter, and it should have either a less than, a greater than, or a not equal to sign, and for that we need wording. If it says more, we have a greater than sign, so mu has to be greater than 30. So researcher studies gambling in young people. She thinks those who gamble spend more than $30 per day. So this is why my null hypothesis is, the alternative hypothesis has a greater than sign. Now, if I draw a normal distribution at this point, and I'm trying to indicate my alpha, so this is where my 30 occurs. The alpha, because it's a more than, is now a one-tail test. And moreover, because it's a greater than sign, it's a right tail test. So all of the 5% have to fall in the right tail. So a confidence interval is now a slightly different picture. So it'll get you slightly different information if you run a one-tail test rather than a two-tail test. A one-tail test, in this case it's a right tail. In order for me to find that critical region or the critical number, you'll go inverse, you'll type in inverse norm, and you're interested in the z-score that corresponds to the bottom 95%. So that's what you'll type in order to find your critical number. The setup of this one is now done, and we'll move on to the next problem. A researcher wishes to see if police officers whose spouse work in law enforcement have a lower score on a work stress questionnaire than an average of 120. So there's my word average, there's my 120. So my null hypothesis is mu is equal to 120. The alternative hypothesis is mu, and then I'm looking for words like lower, which indicates that it must be less than. Here's my null hypothesis, here's my alternative hypothesis. If I want to draw a picture of this representation, the 120 goes here. Now the alpha is a 0.01 one-tail test. But because I have a less than sign, it is now left tail. So the 1% goes all on the left. In order to find this critical number, you'll type in inverse norm of 0.01. And you'll be able to find the place where the critical region is cut off from the non-critical region. So I have a couple more vocabulary words: one-tail test, right-tail test, left-tail test, and two-tail test. One other thing that I wanted to include in this video is the difference between type 1 and type 2 errors. What I found the most helpful is this box. The box is on page 418 if you want to take a look at it in the book. But basically, your null hypothesis is either true or it's false. Now you can either reject the null hypothesis or do not reject the null hypothesis. Now, when in fact the null hypothesis is false and you happen to reject it, you're making a correct decision. If the null hypothesis is true and you do not reject the null hypothesis, you again make a correct decision. When the null hypothesis is true, but you reject it, this is called type 1 error. So this is my type 1. If the null hypothesis is false, but you do not reject the null hypothesis, you are committing a type 2 error. Now, the severity of the errors depend on many things, but if you're interested in proving that there is no difference, so you're interested in null hypothesis to be true, this will basically result in more testing if you commit the type 1 error. If you reject the null hypothesis, says, no, I think it's still different, please do more testing. In a type 2 error, where you're trying to say that it's equal to, and you do not reject the null hypothesis, so no, it's close enough. What might happen is, if it's a medical research, the drug might come out in the mainstream, and then we basically wait until something goes wrong with the person, says, wait, we have to go back and recheck our numbers again. So in that case, the type 2 error is way worse than type 1 error. But if the opposite is true, if you're trying to say that the alternative hypothesis is true, then the severity of the error is reversed. In any scenario, the probability So the analysis of type 1, type 2 error is something done separately, but the probability of type 1 error is your alpha, and the probability of type 2 error is labeled with the letter beta, which is 1 minus something called the power of a test. Now, we do not have software to identify the power of a test. Therefore, the probability of type 2 error will be a hypothetical thing. This is actually the end of the definitions of chapter 8, and we'll start with 8-2, which are actual tests. And the rest of chapter 8 and chapter 9 will be basically going through all of the tests that are included in this book and in your calculator.